Okay, so in this part of our talk, oh fun, people up on the roof, we're going to talk about partial differential equations. And so partial differential equations basically involve more than one independent variable. So some standard partial differential equations that we will talk about how to solve. We might try to solve the heat equation, which is this. Uxx equals to something like k times ut or something like that. K a constant. U would be the temperature function on like a rod. So you'd be talking about something like a rod. And so at a particular point, you can talk about the temperature there at time t. That would be u of xt, all right? And you might do things like you could fix the temperature at one end at any time to be 0, and you could fix the temperature at the other end at any time to be 0. So you could hold the ends at fixed temperature 0, put them in an ice bath or something, whatever, and then you could, if you have an initial condition, an initial temperature distribution on the rod, you could study how that temperature dissipates, you know, how it changes with time. And if we solve this heat equation, then we can find the specific details of that as an example. So these kinds of things are called boundary conditions, right? And then you'd also have to be given u of, say, x comma 0 equals to f of x. So this would be the initial temperature distribution. So for these heat equations, you have a set of boundary conditions and an initial condition. You have to solve for both with respect to the heat equation. Another kind of PDE you could look at would be something like this: uxx plus uyy equals to 0. This is Laplace's equation. All right, and that also comes with various boundary conditions. There's no time in this, so there's no initial condition, right? It's timeless. It's just y's and x's. But this is the differential equation which is satisfied, for example, by the voltage function in a two-dimensional system with no charge. You could solve, let's see, the other thing we look at is something like this. Uxx equals to, how's it go? I think it's 1 over v squared utt. I think that's right. This would be the wave equation. One-dimensional wave equation. Maybe I'd use a y instead of a u there. So this differential equation, partial because it has x and t, both variables, but the solutions would, for example, describe like waves on a string, transverse waves, with the velocity of the waves being v. We could solve all of these using the technique that I describe here, which is a combination of things we already know and the method of what's called the Fourier decomposition. Okay, so I'm going to start by focusing in on the question of how do we solve boundary value problems. I'm going to show you 3 or 4 standard results, and then I'm going to show you examples where we keep doing those over and over again, but I think it's helpful to just take 20 minutes to just briefly go through the standard boundary value problem results. So let's do that now. Bailu, did you actually pan over to this? Okay. Otherwise, I feel silly erasing it. All right, now I'm going to use a projector. So, getting on with it. Those are the problems we'd like to solve, basically. We'll talk more about the Fourier technique when time comes. But first, I'm going to talk about boundary value problems. Here's our first problem. 0 endpoints. So, here it is. Suppose you have y prime prime plus ky equals to 0, subject to y of 0 and y of l are both equal, all right? So I'm not saying that they have to be 0, I'm saying that they have to be equal, matching endpoints, all right? Suppose x is the independent variable, and we're seeking solutions for 0 less than x less than l. The k is a variable. My point actually here is that only when k is certain values is it even possible to find solutions. So if you think about it, there are 3 different cases for k. Either k is 0, k is positive, or k is negative. And we break those 3 cases and look at them separately. K equals 0. Then you got y prime prime equal to 0, right? Which gives us what? Ax plus b is our solution to the differential equation. But y of 0 is b, y of L is AL, so A is 0, and apparently, oh, how did I know? I think I'm assuming that they're both 0 as well here. Oops. Hey. Sorry. I think there's something missing up there. I'm assuming y of 0 equals y of L equals 0. Otherwise, I would also be allowed the constant solution. Right? Okay. Case 2, if k is less than 0, that means you can find a beta such that k is equal to minus beta squared. Then you've got this differential equation, y prime prime minus beta squared y equal to 0. But the solutions to that are cosh and sinh, cosh beta x and sinh beta x, using that characteristic equation we talked about earlier. You get, lambda equals to plus or minus beta. So anyway, it turns out that this is the solution. We actually did that, I think, with beta equal to 1. But anyway, so if you plug in 0, you get A equals 0. If you plug in L, you get B sinh beta L is equal to 0. But the thing about sinh, the only place sinh is 0 is 0. So L not being 0, that means that B has to be 0. And so we find A equals B equals 0, so there's no solution in that case either, except for the trivial solution, which we don't care. We're looking for non-trivial solutions. Case 3, suppose that the k defining the differential equation is greater than 0. Well, in that case, you've got k is equal to beta squared for some positive beta, some real beta, and that gives us y prime prime plus beta squared y equal to 0. Okay, well that gives me lambda squared is plus or minus I beta when I solve the characteristic equation, so that gives me sines and cosines of beta. So I get cosine beta x, sine beta x is my possible solution. Now I fit the boundary conditions. Y of 0 is A. That means that A has to be 0, all right? But y of L, oh come on, stupid visitors. B sine beta L equal to 0. There's nothing to see up there anyway, people. What you doing? Sorry. B sine beta L is equal to 0. Well, how can that be 0? It could be 0 if B is equal to 0, which is not interesting. That gets us back to the 0 solution.
Or the inside is, well, I was going to say 0, but it costs me pi.
Yeah, any integer multiple of pi, right? N pi. So that gives us beta L equals N pi, interesting solutions. So basically you have signs that are tied to 0 at the endpoints. And you can have more and more oscillations between 0 and L, but sines gives you the right thing, provided that you have beta L equals N pi. Now if you go back, what was k? K was beta squared, right? So apparently k has to be equal to N squared pi squared divided by L squared in order to fit these boundary conditions. So this is our result, y prime prime plus ky equal to 0, subject to these being 0. We have non-trivial solutions only of the form y sub n is b sub n times sine of n pi x over L for n equals 1, 2, 3, da 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 da. And the non-trivial solutions exist only for that k being n squared pi squared over L squared. You notice how different this is than earlier part of the course. Like earlier in the course, we just had like a number here. We didn't worry about, oh, if that number is there, are we going to have solutions or not? Because there were always solutions because we were solving initial value problems. Now we're solving boundary value problems. There may or may not be solutions to a given, putting a different given k here. So assuming there are solutions actually forces k to fit one of these values. There's a countable number.
The condition for non-trivial.
Right. You're like, well, how do you run into boundary value problems with a variable k? Well, we'll see that soon enough. This actually is not academic. When we solve the PDEs, we'll arrive at these kinds of problems. You'll see. But I'm just laying a groundwork here. Next problem, a very similar question. Y prime prime plus ky equal to 0, subject to y prime of 0 is equal to y prime of L equals to 0. I forgot my 0 again. Sad, but true. It's a cut and paste problem, I'm pretty sure. I'm missing a 0. Sorry, I told you that one. You can't point that one out. So again, so k equal to 0, again you get the linear solution, and we just get, the only solution we get is just y equals to b. We get a constant solution that could be non-trivial. So k equals 0 just gives us possibly a constant solution. Because the slope being 0 on both sides forces the coefficient of x to be a, which is 0. Case 2, excuse me. If we have k less than 0, k equals minus beta squared. We get Condensed, right? And again, we can argue that the coefficients are both 0, essentially for the same reasons as the last proposition. Case 3, when the k is greater than 0, we get possible sines and cosines. We plug y prime of 0. Well, y prime of 0 makes this become a sine, makes this become a cosine. Cosine of 0 is 1. So this ends up giving us beta b. Oh, I said something wrong here. What? Oh, yes. So b is equal to 0, right? Y prime of L, on the other hand, is minus beta a sine beta L. And again, same song and dance, this can be n pi. So we get beta L is equal to n pi. And again, we get, so this time, but this time we get cosines, because we're assuming the derivatives are 0 at the end. So the derivatives are sines, so we know the sines are 0 at the end if we put n pi x over L and we stick in 0 over L into that, we get sine of n pi when we differentiate. So this is the fixing the derivatives to be 0. So that would be the condition that, for the heat equation, if we're talking about heat equation, that would be the condition that the temperature is not changing at the end points of the rod. So like,
So constant temperature.
yeah. Well, let's see, what does it say? Something like that. Oh, excuse me.
So if you
Oh.
so if you take the derivative of points and it's like a non-zero number, you use the
Yeah, I'm sorry, I shouldn't have got into that. I'll get back into that once a little bit later. I'm sorry. Mixed endpoints, if we have one side is 0 and the derivative of the other side is 0, let's see, then again, we consider case 1, case 2, case 3. Case 1 has nothing because the linear, when you plug in the data, you get 0. Case 2, KB greater than KB less than 0, we get Condensed. Y of 0 gives me A equal to 0. Y prime of L gives me beta B cosh equal to 0, which again, because this is non-zero, forces B to be 0. No solution in case 2. But case 3 is interesting. Again, the cosine and sines. When we plug in y of 0, we get A equal to 0, right? When we plug in y prime of L, we get beta B cosine beta L equal to 0. Now we face the question of when is cosine beta B L equal to 0. So this is 0 for like odd integer multiples of pi over 2. Plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 over pi over 2. It's fast. A nice formula for that is 2n minus 1 times pi over 2, right? This is an odd integer, pi over 2 equals beta L. And so those are the non-trivial solutions for one side being 0, the other side having fixed derivative being 0. And that gives us this proposition. We get sines of that funny value for k being that that particular value depending on n. And then likewise, if I have y prime of 0 is y of L, so if I switch them, I still get cosine. Instead of getting sine, I get cosine of that weird value. So it flips to sine and cosine, but the same kind of half integer value for beta L gives you that pi squared n minus 2n minus 1 squared over 4L squared value for the k. All right. So I said by now you might wonder why we even bother with hyperbolic sine or cosine in these boundary value problems. It seems only sine, cosine, and the constant solution appear non-trivially. Indeed, that is the takeaway message of this section, but for non-trivial and unchanging endpoints, we will find either sine, cosine, or constant solutions. That said, logic requires us to investigate all cases, at least to begin our study. But we will see that hyperbolic sine and cosine appear in solutions to Laplace's equation on some rectangular domain, so don't worry, they'll come back. All right, so now I'm going to show you how we solve a heat equation. All right, here it is. So generically, and I'm going to refer to the Fourier technique as we need it. We'll talk about what that is when we get there. So suppose you want to solve uxx equals alpha ut. Is that, can you even see that, Belu? Is that too small? There we go. Uxx equals alpha ut. Actually, let me write this out. It should be written out. Put this away here. Find my markers. Oh, should I found a printout of these? Oh well. Somewhere in my office there's a printed version of this. I just didn't find it yet. Okay, so heat equation. Let's see. So we've got uxx equals to, let's say, alpha ut, for alpha some constant. Right? And I'm also assuming we have some boundary conditions given. Let's see here. How about we'll assume the first case. We'll assume u of 0t equals u of lt equals to 0. All right. And let's also assume we have u of x comma 0 is equal to f of x for some given initial temperature function. All right. I'm going to walk us through how we solve this problem. Okay. We may need to invent some math as we go in order to make sense of it. All right, but we'll get through it. So the first thing we do is we make a guess. All right, we guess that we can solve this by using a rather simple kind of solution. Our guess is that we can find something like u of, and we're going to have to modify this guess as we go a little bit. Not exactly modify it, but we'll have to see beyond my initial guess. Maybe we have to take our guesses and make a guess with our guesses. I mean, it doesn't look like we have guesses here yet, but it turns out that this is going to be more than one thing I'm finding. But suppose you have a solution that you could write as a product of solutions. Now here, of course, I do not intend the Laplace transform notation anymore. Here X, big X, and big T are just functions, respectively, of X and T. All right, so when I write x prime, it's understood to mean dx dx, okay? And when I write t prime, it's understood to mean dt dt, because that's all it can reasonably mean. All right, that's just the notation we're going to use here. So if I have such a product solution, if I go back to the heat equation, all right, then what does it do? It tells me uxx equals alpha ut just translates into, well, if you think about it, xt, well, I guess I probably shouldn't use the prime notation just yet. So this becomes, partial squared, partial x squared, xt equals to alpha partial t of xt, right? But the thing is that t is not a function of x, right? So this guy just pulls out. And likewise over here, this guy, you could think of as just pulling outside the derivative. All right? And so what this gives me is just t x prime prime equals alpha x t prime. Okay. This general thing I'm doing right now is sometimes called separation of variables. Not to be confused with the other separation of variables, but
Okay.
yeah, I mean, it's similar because we're also separating variables. Let me show you what I mean. So if you divide both sides by xt, okay, so we lost the trivial solution. Oh well, I think we'll get over it. Alpha t prime over t, divide by xt, right? So I've given up on having a trivial solution. Anyway, we know that we could add the trivial solution, but who cares? Well, this is a very interesting equation because this suggests something. All right. So this is something students always are like.
So it's kind of you have big X, the second derivative of big X divided by big X.
Yeah.
That ratio is equal to the ratio of t divided by t times constant.
Indeed, but I guess the thing to take away from this is, I mean, this is a function of what?
Of X.
Of x, right? This is a function of what? Yeah, little t, right? But how can you have equality of a function of x and a function of t?
T multiplied by, well, I mean, there it says it's multiplied by.
I mean, a lot of times in calculus 3, when we're trying to prove something is conservative or not prove, when we come to something like something's a function of x and a function of y, we're like, oh, contradiction, end of story, right? But the reason we say that is because we have a non-trivial function of x, like it's an x or an x squared or something. The only thing that's in common to functions of x and functions of t are constants. Constant functions are, in a trivial sense, both functions of x and functions of t. It forces for this ratio to be a constant. And so in order to keep with the nomenclature of the thing I just had on the projector, I'm going to call that constant minus k. The reason I'm going to do that is because then you can see that separation of variables has in fact given us a pair of ODEs to solve. The one of them being x prime prime plus kx equals to 0, right? The other one of them being t prime equals minus alpha k t. So the t equation I could solve, by the way. I could just solve that. Belu, am I in frame? I don't really care about that constant t naught either, I mean, because, well, you'll see why, but whatever. I mean, that's the solution there. But this other one, this is a, I don't know what k is. That's the thing. This brings us exactly to, where are my chips?
Tortilla.
Oh, tortilla. Oh,
It's really good.
it's really good. Yeah, I won't do it. There's too much noise. The sound of me eating chips on the microphone won't be pleasant. So guys, my point to you is this is why we have to care about those boundary value problems. I mean, this separation of variables naturally brings us to the question of like figuring out, can you solve this for arbitrary k, right? But we're given boundary conditions, right? Now, I'm not given boundary conditions for x. I was given boundary conditions for the temperature, right? And x is like part of the solution which makes up the temperature function. It's not the temperature function itself. So what I need to do now is I need to take these given boundary conditions and translate them. What does this say? This says that x of 0 times t of t is equal to x of L times t of t is equal to 0, right? But look at what t of t is. T of t is some constant times an exponential, right? If the constant is 0, then we're back to the 0 solution. We're not looking for that. So we can assume that t naught's not 0. T naught not being 0 means that but t of t is not equal to 0 implies that we have x of 0 equals x of L equals 0. Aha! And then we know by the first proposition we went over in my PD chapter that we can work it out, and that says that x of x is equal to some constant, let's say a sub n times what? Sine of n pi x over L, and where k is equal to what? K is equal to, what is it?
Is it,
I think it was n squared pi squared over L squared. Let me look it back up. If I had half a brain, I'd have a printout of this while we're doing this. Yeah, k was n squared pi squared divided by L squared. It's by proposition 8.3.1 in the notes. Okay. On page about 202 currently. Yeah. I used a b sub n, but that's kind of immaterial. And I might stick a little sub n on this, you see, because apparently I get a different solution for each n, right? I found not just one solution. It looks like I found a whole lot of them, right? So I went looking for one solution, but if you look at what we have, we can construct a formal solution. So formally, and which is just a lazy way of me saying I am not worrying about the analysis here, take it or leave it. Something like this, the sum n equals 1 to infinity. Oh, by the way, so that makes this what? T naught e to the minus alpha n squared pi squared t over L squared, right? So I have some constant a sub n times the sine of n pi x over L e to the minus alpha n squared pi squared t over L squared. And this solves uxx equals alpha ut subject u of 0t equal to u of lt equals to 0. So subject to the boundary conditions. And I mean, for coefficients a sub n chosen such that this thing actually converges, of course.
So in the basic, the reason that's 0 at the endpoint is because sine of that whole thing right there.
Yeah.
Is
Sine
like
of
0 or 1. I mean, not 0 or pi or
0 or n pi. It's 0 if you plug in 0. If you plug in x equal to L, you get sine of n pi, which is 0. Yeah.
Okay.
That's why it works. But of course, logically, there's like 3 different cases to check, but you can sort through them. The only thing that appears non-trivially is just these sine solutions.
Okay.
So it's not guessing. It really is, deriving. I mean, the guess is back here. This is the guess. And then from that, I can get everything else. Now, what have we not done yet? I have said nothing about how to get our hands on the initial temperature distribution. This right here. Right? So now I want to talk about that initial temperature distribution. I'm going to keep my formal solution. I'm going to erase everything else because I don't need it. I just need the formal solution for the discussion now. Somebody erase that, hopefully without getting into trouble. Actually, Bailu, I'll regret it. Let me work over here. So generically, we have u of xt is equal to a sum n equals 1 to infinity. Some constants, I'm going to choose them to suit my purposes before you know it. Sine of n pi x over L, the exponential of minus alpha n squared pi squared t divided by L squared. And that's it, right? Right, formally. And now we want to fit the initial condition. What was the initial condition I wanted to fit? U of x comma 0 equals to f of x, right? So what does that say about biformal solution? If you look at u of x comma 0, what happens? You get the sum n equals 1 to infinity of, well, a sub n sine of n pi x over L. And guess what happens to the exponential? E of 0. What's E of 0?
Oh, what's E of 0?
Right.
Yeah.
Because I'm plugging time equal to 0 into here.
Oh, yeah.
So those are just 1.
Yeah.
So it just leaves you that, right? You're like, well, that doesn't really help me. So but this has to be equal to f of x, right? I mean, that's kind of like, okay, yeah, and what? Then this, in order to actually make sense of this equality, this is where we need the Fourier technique. So here, we need the technique of Fourier series. So what is the Fourier technique? Fourier's observation, as it applies to us right now, is that f of x can actually be written as a sum, n equals 1 to infinity, of, let's say, I need another letter, let's say b. Although I really shouldn't use a sub n and b sub n. They tend to have reserved meaning in the notation of a given differential equations book, but I'm not trying to link with those, so just keep that in mind. B sub n sine of n pi x over L. You're like, what do you mean? I mean, for a given f of x, you can expand it as a sum of signs with appropriately chosen coefficients. These are called the Fourier coefficients. Of f of x. Now, it happens to be that they're also the needed coefficients up here, because once you have f of x written in this way, you actually can equate coefficients of like, matching signs, and so you'll end up with a sub n is equal to b sub n. Okay, but there's a standard technique to calculate these b sub n's. Let me show you how it goes. So the critical thing here is something like this. If I was to integrate from 0 to L, let's see here, sine of n pi x over L times, let's say, the I think it's this, sine of n pi x over L well, this would be easy. This would be the integral of from 0 to L of 1/2 1 minus cosine squared n pi x over L dx. Excuse me. Because that's sine squared. And that's the half angle formula for sine squared. It's not cosine squared, it's cosine, I'm an idiot. Cosine of 2 n pi x over L. Yes, duh. And then, of course, the cosine integrates to sine of 2n pi x over L. But when you plug in 0 and L into the integral of this term, you get 0. So let's just be done with it. That goes to 0. And you're just left with this 1, right, which gives me L over 2. So if I was to say, and by the way, here's the other thing, and I'm not going to prove this, but it's true. The integral from 0 to L of sine of, let's say, n pi x over L times the sine of k pi x over L dx, this is equal to 0 for n not equal to k. Long story short, there's a trig identity which says that this can be written in terms of a sum of cosines of either k, basically n plus k times pi over l, or n minus k times pi over l. You get cosines. You get two cosines that are kind of like this added together. There's like a half or something. The point is they both integrate to sines of things like this, and so they drop to 0.
Okay.
This is the only case when they're equal that you get something not equal to 0. But this kind of looks like a dot product, right? Like, I mean, this is a lot like those inner products we were doing in linear, where, you know, I mean, so there's something very much like a projection here. In fact, it is. I mean, that's one of the examples that I gave. But as you can see, it doesn't. I mean, there's the dot product of it with itself is L over 2. There's some kind of, we have to take care of that. Long story short, so if I integrate both, Bailey, are you getting this down here? So if I integrate from 0 to L of f of x times the sine of, let's say, k pi x over L dx, right? What do I get? I get, right. So the b sub n, right? And then the integral from 0 to L of sine of n pi x over L, sine of k pi x over L dx, right? Assuming that I can bring the integration inside the series. Ooh. Yeah, well. Anyway, there's analysis we're glossing over here. This is 0 in every single stupid case except for one, where k is equal to n. So this just gives me b sub k times L over 2. And so therefore, I find the formula for the Fourier coefficient b sub k is just equal to 2 divided by L, integral from 0 to L, f of x, sine of k pi x over L dx. So in order to solve the heat equation problem, all I got to do is take my initial condition function, calculate these Fourier coefficients, and stick them back into the formal solution, and that's the solution to the heat equation.
Okay. So, and the b sub k, those taking place at the home asymmetric.
Right, exactly. By comparison, in fact, I just put these values back up here. Well, eventually I put them back up here to get the equation, which has time and position dependence. Okay, so let me show you, see if I can find an example with that worked out to look at. You got it? Can I?
You're good, yeah.
So, once I get it up here. Taking a step back from the problem of the Fourier determination, I would just point out that if we had gone, the other route, if we had the ends so-called perfectly insulated, if they were both with ux equal to 0, essentially the same argument would have brought us to a formal solution like this, right? And then we would have needed a Fourier cosine series to fit f of x because you have cosines. If you did the mixed endpoint, you would end up with this, right? And I guess you still need a sine series. I don't. been a little while since I worked some of these. All right, do I actually have one? Oh, here we go. This one's kind of cheesy. Problem 2. I'm given, you'll see why I say it's cheesy here in a second. Or maybe it's not, I forget. Let's see. Anyway, I've got ut is 5uxx, all right, and 0 boundary conditions, and initial condition of 1 minus cosine 2x. Okay. So we go through the same thing we just went through. Eventually we arrive that we need to solve this 1 minus cosine 2x is this to find my b sub n's in my formal solution. So then I need to calculate, my L here is equal to pi. Okay. That's nice because you notice you've got like n pi x over L. So when I take L equals to pi, it's very nice.
It just reduces.
Yeah, I just end up with nx everywhere, which makes the calculus a lot easier to look at. Yep. And so I need to calculate this for the given f of x, all right? So the given f of x is 1 minus cosine 2x. And so first of all, I observe that 1 minus cosine 2x is an even function. And so that implies that the b2k are equal to 0. You can see what's that? pH 134, which is posted on my website for the details of that integration. But this is the non-trivial part. So I have to integrate 1 minus cosine 2x times sine of 2k minus 1. And when you do that, you get that lovely bit right there. So this is what you get. And so then that means that I plug that in for my b sub 2k minus 1. My solution, that is k equals 1 to infinity, 2 over pi. That's the 2 over L term. Here's the b sub k. Here's the sine and the exponential. Notice that n is 2k minus 1. The even n's are not even. They're all trivial. So there's the Fourier coefficients are 0 for the even n. So you only have odd n's appearing in your solution to the heat equation. And there you go. That's an honest to goodness solution to a heat equation. As you can see, there's a lot involved. I mean, the hardest thing in all of this is the Fourier calculation. The actual integration of the Fourier coefficients is kind of a pain. It's Calc 2. Here's another one. This one's actually cheesy. This one would be reasonable for like an ICE exam or a final in class because it doesn't require actual Fourier calculation. It doesn't have that hard calculus 2 aspect to it, right? You just have to understand the big picture of how we're solving these, and then you could. So I get a formal solution again. Okay, so what do I got? I got. Do I have mixed? Was that really it? Did I really do that? I'm claiming mixed boundary conditions. Okay, fine. That's what I did. That puts us in case 3, which means gives me this generic. Boundary value solution, and but L is 1/2 and alpha is 7, so my formal solution simplifies to just this. The initial data though is u of x0 is sine pi x plus 42 sine 17 pi x. That when I plug in 0 makes this go away, so I've got to match this to that somehow, right? But I don't really need to calculate the Fourier series for this, because it's already a Fourier series. That's what makes this cheesy. There's no Fourier calculation because the given initial temperature distribution's already in Fourier decomposition, already Fourier decomposed. That's why it's a kind of cheesy problem. But it's also nice because you can just read off b sub 1 is 1, and b sub, let's see here, how do I get 17? I need 18 minus 1, right? That's n equals to 9. And b sub 9 is 42. Okay. Yeah. And so therefore my solution is simply sine pi x times e to the minus pi squared t over 7 from n equals 1 plus 42 sine of 17 pi x exponential of 17 squared, which is 289 pi squared t over 7.
And that's because you already have it's already in like terms of sine.
Right. So I got around the trouble of finding the Fourier decomposition in this case. Yeah. Excuse me. All right, so then you can talk about how to solve wave equations. So looks like that, partial squared y, partial x squared, 1 over v squared, partial y squared, partial t squared. So it's kind of like the last one. What you do is you assume that you can write the solution as a product of x and t. You plug it in. It leaves you to x prime prime over x equals 1 over v squared t prime prime over t. And again, I'm going to set that equal to minus k, so I could use the first part of my chapter to kind of reason through it for the given boundary conditions. I've given boundary conditions that basically the string is fixed at position 0 at 0 and L. So the string is between y equals x equals 0, x equals L, the endpoints. So, and then you're plucking the string and it's like waving between those 2 points, but those 2 points are fixed. But that makes us face x prime prime plus kx equal to 0 and t prime prime plus kv squared t equal to 0. So this time, solving the t is also going to give us non-trivial sines and cosines. It's not just going to be an exponential with the t with the like with the heat equation, but still, I think the determination of k is going to come from looking at the boundary conditions applied to the x part of the solution. Like we again get x of 0 is 0 and x of L is equal to 0 from the assumption that y of x0 and y of L0 is 0, because it's true for all time, it's true for time 0, and by non-trivial of the time 0 solution, we have to have that those are 0. That leads us to x of n is sine of n pi x over L by case 1, start of the chapter. And so that means that k, n squared pi squared over L squared, I plug that back in to here. Can we see this, Belu? Can I see this too? Okay, plug it into here, and then I've got, this second order differential equation with constant coefficient. The constant coefficient's ugly, but I know what to do. That's t prime prime plus beta squared t, where beta is v n pi over L. So that gives me a sub n cosine beta t plus b sub n sine beta t for my solution. And the product of that and the x is the nth formal solution. So here's what that looks like. Y sub n xt is equal to a product of the sines and cosines in x and t respectively. And and then of course I have one of those for each value of n. And so in order to fit an initial condition for the wave, how it's plucked originally or whatever, I need not just one of these boundary solutions, but I need a sum of all of them in order to take care of the different initial conditions. It's interesting. So at the start of the course, for a second order problem, we have to have a C1 and a C2 in order to fit initial conditions for a given ODE, second order. Now we find ourselves with a PDE where we actually need essentially like infinitely many constants to fit, infinitely many constants in order to fit different possible initial conditions. Because the initial condition, it's not just a position and a velocity at one point for one variable. It's the totality of the shape of the string between the 2 points. It's infinitely many data points, which is why we need these infinitely many constants, as is interpreted through the Fourier decomposition.
Because each Fourier term is one initial condition.
Yeah, like
and
that.
You sum it up, and you have to sum them all together.
I think that's the right way to look at it.
Each piece of n is
Yeah.
Okay.
That's an intuition for it. Now, there's all kinds of analysis I'm glossing over, I will admit. Okay, so that's our formal solution in the sense that I haven't shown it converges. And then to actually find a specific solution to the wave equation, I need to be given an actual initial condition. And then I can fit that initial condition to the sum of sines and cosines, again, by the Fourier technique. Not quite the same one, though. So if I have g of x0 as the time derivative, there's different things that can happen. Let's see if I can find a specific one.
Dr. Cook,
Yeah.
like you were talking about when we first started this part, like the different cases and all that stuff.
Yeah.
Those are determined by the initial conditions that you define in the problem.
Which cases are we talking?
Base and endpoints, basically.
The endpoints, that would be the boundary conditions.
Yeah, boundary conditions.
Boundary conditions are fixed, and then on top of that, you have to be given sort of an initial shape for the string, which would be the initial condition. Or you could be given an initial, like, maybe you need both. Maybe you need initial shape and you need initial speed. I forget. I think maybe you actually need two initial conditions. Let's look at this one. So here's a wave equation, ytt plus 4yxx. We're looking at the wave between 0 and pi for x and for t positive. And we're given boundary conditions that the endpoints are fixed at 0. An initial condition, y of x0 is x squared times pi minus x. And also an initial velocity. That's right. I need the initial shape of the string and also the initial direction in which the string is moving at each point. I need both of those things to solve this. That's right. And y of t, dy dt, x comma 0 equal to 0. So it's initially like frozen, I guess. So you go through the formal solution, get that, and then if you plug in time equal to 0, what happens is for the when you plug in y of x0, this piece goes to 1, and you're left with a sub n sine n x. But this piece is gone, because sine of 0 is 0. So the y of x0 needs a Fourier sine decomposition, right? On the other hand, the derivative picks up also a Fourier sine, but these b sub n's, right? So I end up needing to decompose both of the initial conditions in terms of a Fourier sine series. So I do that, and I do that for the other one. Where is it? Where is it? Where's my t? Sorry. Why am I not doing anything y of t x 0, 0? What? Whoa, man. Come on. Oh, I'm sorry. I missed this sentence. It turns out that this initial condition is rather boring because it just implies that the b sub n's are all 0 for all n. Okay, so we actually got out of it's only half of the problem. In general, you'd have to find the Fourier decomposition for the initial velocity function and also the initial position function for the wave. This one just has to find for the initial position function, and here that is. But again, it's the same song and dance basically. 2 over pi, integrate the given initial position function times the sine, but it's ugly. I mean, this is integration by parts twice, right? I mean, it's nasty, but you can do it. And out pops those coefficients. You plug them back into your general solution. Bammo, that's the solution to the wave equation. Just like that. They're not impossible. They're not actually even that hard, but they do take a considerable amount of persistence to get through a full problem. This one's kind of cheesy because here my initial position and initial velocity functions are actually already Fourier decomposed. See? Sine x, 13 sine 4x, 7 sine 5x.
Yeah.
So that makes it easier. In this one, so basically I have, it tells me a sub 1 is 1 and a sub 4 is 13. And then the b sub n's come from, now the differentiation, the yt, you got to be careful there. When you differentiate the t, it pulls out a 2n from the formal solution. When you differentiate it, it pulls things out of the t solution's arguments, because you don't just have sine of t, you've got like, or cosine of t, you've got like sine or cosine of multiple, like I think this one it must be 2nt, so you pull out a 2n by the chain rule. And so you don't get direct comparison of the coefficients of the b's and the coefficients of your given initial velocity function. You have to adjust a little bit. In this case, I see that b sub 5 is 7/10, I think, because I get 10, b sub 5 is equal to 7, comparing. So anyway, altogether, this is the solution to the wave equation. As you can see, this example would be reasonable to put on a final exam or something, because really, if you understand the general formal solution, even if you don't have enough time to calculate Fourier coefficients, if they're essentially already given to you, you should be able to do it, yeah. There's also something called the D'Alembert solution is elegant and magical. You'll read it in the book. It doesn't involve any of these techniques, and yet it can solve some of these problems. kind of special. Laplace's equation, phi xx plus phi y equal to 0, same song and dance. We assume that you can write phi as like x of x times y of y. You stick it in, you get this, you divide by the product xy, you get xxx over x prime prime over x equals minus y prime 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 over y. So if you think about this, right, if x is sines and cosines, this is coshs and sinh. If this is coshs and sinh, that's sines and cosines because the k is opposite. I mean, basically, in some sense, the quote-unquote k is opposite, right? So like y prime prime minus y has solutions cosh and sinh. Y prime prime plus y has solutions sine and cosine. So there's always going to be this kind of like mirroring of coshs and sinh and sines and cosines for the Laplace equation, two-dimension rectangular we're talking about. So here, in particular, this one I'm solving on the rectangle, 0 pi. Gee, I really hope that the x is the one with sines and cosines. That would have been nice because I put the pi in the x. In 0, 1, that's the y goes from 0 to 1. I want to solve Laplace's equation subject to the boundary conditions. U of x1 equal to 0, u of x0 is f of x, and when we put x equal to 0 or pi, we're at 0. So what that looks like in a picture, it's good to have a picture here. Bailey, can we see this? So here's x equals to 0, here's x equals to pi. Where should I write, Bailiff? Right here, just another marker. So here is x equals to 0. Here's x equals to pi. Y equals to 0. Y equals to 1. So what we're saying, again, think of phi being the voltage function. Oh, sorry, that's physics 2. Oops. Eventually you'll learn what voltage is. So when you do, think of it being the potential energy per unit charge, if you like. Or you can think of it just being potential energy for a conservative force, if you wanted to. Anyway, I'm assuming that that voltage, or potential energy, if you like, is 0 along x equals to 1, x equal to what? X equal to 0, x equal to pi, and y equals to 1. But then on y equals to 0, this guy down here, we're doing something interesting. There I'm saying there's some kind of interesting phi of x comma 0 is equal to f of x. Okay, so down here on this bottom boundary, I've got some kind of interesting voltage distribution. So then the question is, how does the voltage function change throughout this whole rectangular grid if it obeys, Laplace's equation? So, of course, I can't really. If I could draw three-dimensionally, I guess I could picture it. Maybe. So, if this is a picture, maybe the potential function looks like this here, right? So, intuitively speaking, I would expect something like. I don't even know. What does the potential function look like as you go over, drawing the value of the potential vertically? So this would be like the f of x is given on that edge. And the question is like, how does the potential change as you go out there? If it satisfies the Laplace equation. All right, so separate variables. Then you face this. We have 0 here and here. That basically that forces me to use sine for x. By part 1 of the first proposition of this chapter, we get x sub n sine x. There's no pi because L is equal to pi, so the pi over L became 1. Yeah, so that's nice. And then, on the other hand, so we have that the k is equal to, we end up with y prime prime minus n squared y, right? Y prime prime minus n squared y equals to 0, which gives me coshs and sinh, right? Oh man, markers are wobbly. Still enough. I wish I was taller. Oh well. Sinh.